Ooh. This is really bright. Do we have the dark mode installed? How is dark mode enabled? But this, am I missing something? Much better. Okay. All right. So, on the previous stream, we got a bunch of things animating in our game. So in our sliding puzzle game, we well, let me zoom in a bit. Let's see here. We got these tiles animating, which is a positive. However, and each time we begin the game, there's going to be a different configuration. Right, the corners here are pink and orange, but if we do it here, it's like different color, like a peach, and that's not even a peach color, a different orange and like a green, etc. So like behind the scenes is some kind of shuffling algorithm. Since the source code, since the standard library is of course open source, we could just like, I could just like include it in the code for this game directly, but I kind of want to do my own version. I want to learn what's happening anyway, and since eventually we're going to be transferring this game into the Serenum that doesn't have a Zig standard library, that means that yeah, it's something I want to learn, so I'll learn it now. Okay, so let's just create a new file called like Fischer-Yates.zig, and yeah, let's try and learn this algorithm and verify that we've learned it by writing it in code and printing it. So how does this thing work? Yeah, shuffling a finite sequence. The algorithm takes a list of all the elements in the sequence and continually determines the next element in the shuffled sequence by randomly drawing an element from the list until no elements remain. Oh, that's really kind of easy to do then. I feel like that's all I need to read and we can immediately implement it. Maybe there's something a bit missing. Okay, so Donald Knuth, a famous computer scientist, described his algorithm P. When exactly did he publish this again? 1969. 5 years later. Wow, really, it was just like, it's like so wild. Like this is a date, like this was like before Dark Side of the Moon, like before Gravity's Rainbow, like before so much of the 70s, which already feels like it was a long time ago. Yeah, need the article acknowledge this. They may not have been aware of it. Okay, so Dunstford had a more efficient algorithm. Okay. Okay, so there's some way of reducing it to ON instead of ON squared. But what's like I guess we should, like, in some sense, I could like read like the lines following this and kind of spoil it, or we could try and figure it out. Because yeah, initially, yeah, so this idea of just you go through the entire list at each step, you just like, you end up having to go through the entire list. You can just do that n squared. Yeah, how do you do this O log n? This is an interesting exercise. In either case, for this game, doesn't really matter since we're shuffling at most, I think like 25 things, so it's not, the timing is not an issue, and we're shuffling it at once, so the timing is not an issue. But should I spoil this and read them what an algorithm? Or not, we can just do like the crude one, and then as a reward we can see let our subconscious think about the efficient one. Maybe a bit later we'll have a look at the like, this is a fun exercise I think, to think about what the O log n version is. For the moment we'll just do the standard one. So we'll just do like crude O n Fischer-Yates. So we're going to say like, what's the idea? See, the idea is simply, yeah, at each stage, randomly pick an element to be like and like unselected element to be the like next. So yeah, construct a list by at each stage randomly picking from the like what's the best way to like phrase this? I want to say like given one list, construct a second list by randomly picking items from the first list. I thought maybe that's the easiest way. Given a list, construct a second list by randomly picking items from the first list. By randomly, I think picking is removing is better. Okay. Sure. Okay, so now this is the question of how do we actually like randomly pick an item from the first list? Ooh. This part is a bit more unclear. So certainly if we had a way of generating a random number between 0 and n, for instance, then we could certainly do this. So maybe the problem boils down to that. Like, how do we generate a pseudo number generator to begin with, and then how can we use that to sufficiently pick something random between in a range. So I guess we have a question is picking a random integer between 0 sort of and n for some n, reducible sort of imply an integer, a random integer can be chosen for any range. I feel like the answer is yes, and I think this could be done. I feel like there's a way to do this easily as well. What would this be? Like, I think a canonical, like a seemingly easy answer is to do something with like modulus, but I think technically you need to be a bit careful with like the kind of ending bits. Like, I think it's incorrect to say, oh, if you wanted to choose like, you know, a like random like 0, if you needed to like choose between the range 0 to 1, if you have to if you have to randomly like flip heads or tails, then you know, just pick like a random number from like 0 to 10 inclusive and then take a modular of that. And it's like, well, in that case, no, because you've got like 6 even numbers in that range and 5 odd numbers in that range. So the probability is biased. You need to choose it between 0 to 9 inclusive, and then you're fine. So is there a way of doing it exactly in general? This really should be a yes. Oh, maybe you could do this somewhat easily by just doing repeated draws. Like, you simply say, yeah, if k is less than n, randomly pick something from 0 to n. If it's greater than k, discard that trial and just do it again. And just keep on doing that repeatedly until something falls in the range, and then you're fine. So we can say, yeah, yes, if yes, easily, if k is greater than or n. Just pick random 0 to n, discard, and try again if the random is greater than k. And then what happens in the case if k is greater than n? Do we also have like an easy solution? I feel like you could do something with, like, the idea is like powers of 2. Like, you would just like randomly choose bits until like the power of 2 you've got is like larger than n, and then you simply apply the same kind of rule. And again, there's probably some really efficient way of doing it, but I really should say like if n is greater than k. We can say choose m such that n to the m is greater than k. Randomly choose digits of n to the m. Apply same idea as above. Okay. Theoretically, this will be fine. What's happening? Oh, Microsoft! When I want to adjust the keyboard, why can't I see a noticeable lag in the frames popping up? This is not acceptable. Totally unacceptable. It's so bad. It's so bad. Just come on. Is there a lag when I press a button and the tile moving? No, it happens the same frame. The same frame. Bloody Microsoft. They can't. Anyway. I bet like when I'm adjusting the keyboard like this, like some JavaScript code is being like called because anyway, as above. So we need to okay, so that at least confirms the idea that you're randomly picking. If we can say like we can randomly choose a byte, then we'll be fine. So maybe now the goal is to create a pseudo random number generator to generate a byte. And then once we do that, we can then just we can shuffle the list as much as we want. And actually, in fact, like we could just apply the modulo idea, provided we just like we kind of go down from the end of the range until we get to. You just have to do like the yeah, it's the idea is clear. Like if you did want to choose like a heads or tails, and you had the random number generated from 0 to 10 inclusive, you would just say ignore the 10, so randomly pick a number from 0 to 9 and then do the modulus, and then it's fine. And then you don't need to do as many trials as just saying it's either 0 or 1. So yeah, we might end up doing something like that. But for now, okay, how can we write a pseudo number generator for a byte? This I'm totally unclear on. Yeah, I don't. Actually, in some sense, I think we could get away with just using the last, getting a timestamp in nanoseconds, and just getting away with the last byte worth of that info. Like it's, again, we're not like, we don't care about cryptographic security. Nothing cryptographically secure would be using like a timestamp probably at all. So yeah, I think we can do this. Or just choose the last byte of a nanosecond timestamp. Okay. So let's then do this. So so let's first write like a like get generated call it R byte, get timestamp, get super pseudo. Being silly now. Get random-ish byte. If we're going to do this with a timestamp, we may as well set up a global timer. So let's see. In standard.time.timer, we want to init this. How did we do it in in our other program. Oh yeah, this variable should be undefined for 1. And let's just call it stopwatch. Stopwatch. Wasn't it just like stopwatch dot init? Oh no, we have to call it on start. Okay. Stopwatch is equal to standard.time.timer start. Then we want to get the maybe that's kind of enough, actually. Ooh. No, if we're like randomly getting this thing at the beginning of the program, it's going to be like highly dependent on using a stopwatch like this is silly. What am I talking about? We simply want to just read the raw time. So how could we do that? Presumably the timing hasn't changed that much between SIG libraries, but just in case it has. Search nano. There's a micro timestamp, and okay, let's zoom in on this. Yeah, calendar timestamp in nanoseconds relative to this thing. Very much, like obviously it's a system call. Now I'm just like worried, could it be the case that like a huge amount of rounding happens in some way, that the last byte's always like the same depending on the operating system? Right, it says like file time has a granularity of 100 nanoseconds. So maybe actually a like micro timestamp might be better. And then we can just use the last byte of that. Yeah, so we do standard timer dot micro timestamp. Get rid of this. So we're going to get a random-ish byte. So we can say micro timestamp is equal to standard.time. Why did I close it when I forgot the name? Micro timestamp. Okay, so this is going to be a I64. I don't have to deal with all of like the Zig extra stuff that comes with doing modulus on signed integers, so we can just bitcast this. Or maybe just like timestamp. Call that micro timestamp, then we can just say converted timestamp. And let's just bitcast the micro timestamp to this. Then we can say the quotient, or rather the remainder. Remainder is equal to the converted timestamp mod Well, hang on. We can we don't need to, we're adult programmers. We don't need to do like division here. You know, we can just shift bits. We can just shift these bits by what 56, and then actually Zig might throw a tantrum if we're I wonder if we can actually just incast it. Possibly can. I'm not sure what the Zig behavior is if we cast an integer that's too big. Like clearly smaller types coerce to larger types, but going down. I should really know how Zig does incast. Let's just look it up now. There's no time like the present. We'll see if the documentation contains it. Okay. Actually, attempting to compare numbers out of range results in safety-protected undefined behavior. So I guess in this case here, it will fail it, and it looks like that's what's happening here. Integer cast. Okay, we are gonna have to, because it's like, this is why I really love Zig. For stuff that's like unclear, Zig's just like, nah, you're not going to get away with it. You need to tell me what you're doing. You need to decide for yourself and then have that in the code. And so we're going to have to truncate it. Always truncate significant bits. Great. This is exactly what we want. Okay. So here, instead of incast, we want this to be truncated. Let's see, if it's A, C, D, it should be left with C, D. Yeah, great. Okay. So let's just... I was going to say, like, get some examples. It should be fine. So let's say R byte is equal to get randomish byte, and then we simply R byte this. Okay, so now we want to do Zig run, Fischer-Yates Zig. Oh, I don't want to have to like run this each time. Yeah, these kind of, I can't, it's still gonna be a while before the new backend is on Windows, but I know that like I went through the hassle of like dual booting my laptop. I don't necessarily want to do that to this desktop machine. Maybe I'll just stream from my laptop next time. But yeah, this kind of looks, again, like random-ish enough to me that this seems to be fine. Okay, so we're getting that. And then, so now once we've got that, we then want to use this to pick a random integer from 0 to a number. Get random I want to say like PN for like positive integer. Get random-ish int range. Okay, maybe get random-ish. Yeah, this is fine. And really the range is like from 0 to something. Get random-ish int up to. So we'll have a limit which is a U8, and then we'll return a U8 that contains this. Maybe like get random-ish U8, random-ish byte up to. Yeah, return a random number from 0 to limit, which is less than or equal to 255. So, how do we want to do this? So we could just do like the randomly pick a number repeatedly that I'm not a huge fan of. Also, just like polling the system for like that many timestamps feels like a terrible. Again, not that performance matters in this case, but not a good performance practice. So let's try and do the modulo idea then. I wonder if we could even make the limit comp time. Not that that would matter that much. So I think we just want to. So let's like do the even and 10 example. So as an example, e.g. 0, this is where I really like the Odin range syntax. For mod 2 should go for limit we'll make the limit strict. For limit equals 2 should be 0 to 9. It's otherwise more even than odd. Okay, so in this case, say we were passing 10 and 2. How do we then determine that we want to be working with a 9? I think we just like choose the current limit, which is the byte, and then just go down until you find like a whole number divisibility, and then you simply -1. So I think what we want to say is we want to get a remainder. Which is the 255 once we get the limit, and then we want to say the OK range is equal to the 255 minus the remainder minus the 1. I guess the computation is left to right associative, so we should be fine. And then actually it's just, while that's the case, it doesn't hurt to write that. Or OK range limit. Then we want to do then we want to pick like, we want to have a loop where we pick like a randomish byte, and if it's greater than the OK range limit, we do it again. So we'll make the R byte 0. And then while true, you want to say R byte is equal to get randomish byte. And then if the R byte is greater than the OK range limit, then we're gonna like continue. So it's rather like if the R byte is within this, then we just like break from this, and then we want to say the random thing is equal to the random byte. Now we do the actual proper quotient of the limit. And then we want to return this. Okay. Simply my head looks a bit too complicated in code. There are certainly more efficient ways of doing this, but this will work for this arena. So then let's likewise change this to get like int, get randomish byte up to, let's just try like 3, or yeah, 3, and then we should just get like 0, 1, or 2 in about like the correct order. 23 undeclared. Okay, 0, 1, 0, 2. We'll have to do like a lot of trials. Actually, how many trials would we need to do? What would like the mean, the central limit theorem predict? Anyway, maybe this is enough. Is that 5, 5? There's 15 here. 1, 2, 3. So 4 zeros, 3 ones, and then everything else is a 2. I mean, this seems alright. I think this is fine for our purpose. Okay. Okay, great. So I guess now we have a way of getting a randomish byte up to a number. We can I kind of realize now that doing the Fischer-Yates will be flawed because like successive random bytes we choose are going to be really dependent on the timestamp. Like the initial timestamp will kind of determine what happens everywhere else. But again, maybe that's fine just for this web case. Another option would be getting some like actual random numbers and then like randomly choosing somewhere in the index to start. But not a huge fan of that. Yeah, I guess this is like doing this now is like what makes it clear why these pseudo random number generators exist. Like you initialize them once with the timestamp and then like that's it. The algorithm needs to be based on that or you're gonna get screwed by timing options. So yeah, if we are doing Fischer-Yates for 16 tiles or 25 tiles, we're going to get a lot of those nanoseconds will be the same, or microseconds. Maybe it would be useful looking at some simple pseudo random number generators. I see like the word caution somewhere. Caution is sometimes required. The list of widely used generators should be discarded. That should be discarded as much longer than the list of good generators. Do not blindly trust the software vendors. This sentence is so telling about modern software. Actually, let's just like screenshot this entire thing. Say this is like progress. Consider the widely used language Java. We'll see if Java's around in 40 years. Up until 2020, it relied on an LCG. Oh my goodness. I wonder how many people wrote cryptographic applications using this. Oh, this looks like there's some cool math in here. So Wirral sequence. This is like fun mathematically, but still trying to think. Like there's something to balance between having just like a simple amount of code to generate something random versus... Oh, hey Sam, thanks for dropping by. Yeah, it did take me wide internet. People had to come around and holes were drilled in the wall, but it's now working. Thank goodness. It's been a while. Yeah, I think I'm currently struggling just between deciding how like actually random to make something for a game versus the amount of code for it. Yeah, so Fischer-Yates is a algorithm to randomly shuffle elements in an array. And like from what I understand, it's actually really simple. It's just, given one list, you construct a second list by just randomly removing items from the first list. That's all it is. And so eventually I want to have something like this in some Serenum code. And so I was just thinking, what's like a simple way to do it in Zig? And so the thing I'm doing is absolutely not cryptographically secure at all. I'm just saying, get a random byte by just choosing the last byte of like the microseconds timestamp. From that, you can just define a simple function that will randomly give you some number from 0 up to a limit. And then once you've got that limit, I could then say, I could then start doing the Fischer-Yates, but all of these, if I continue to poll the time each time, the microseconds aren't really going to change too much. So then these bytes that I'm getting are not really going to... Yeah, and like the so-called maybe the very first random byte I get is somewhat random, but then the ones that follow after that are going to be quite deterministic. So yeah, so now I was like going down the maybe rabbit hole of looking at a pseudo-random number generator that would get something somewhat random once I plug in the byte from a microsecond timestamp. And I'm just wondering how much effort I should put into decoding that. I feel like I should do it just because I want to understand at least what one of them is. But yeah, Scholarly Journal Wikipedia is telling me that it's important to be very careful when selecting any kind of pseudo-random number generator. And that, like, apparently, like, in Java up until 2020, probably like in the standard library, they were using this like linear congruence generator, which was of low quality. So yeah, in a programming language that has been around for 30 years, something of low quality was in there. So, well, okay, for 25 years. Yeah. Okay, so maybe we should just try this Mersenne twister, discuss below. Okay, but how are we meant to determine from this list which are the high quality PRNGs? I feel a bit sad that I see von Neumann and then it's like it is of poor quality, but like I guess if von Neumann, if you're the person making the first one, then it's okay. Like you come up with the idea. Yeah. The xorshift is one that's that I actually was using in the current in this current really simple sliding puzzle app that I'm making. Like yeah, the game itself is just looks like this at the moment. Something that should be really easy to code and transfer, to code upon the Serenum, maybe even in a performant way. And yeah, for that, the pseudo random number generator for that was the Xoshiro here. I guess I can just look into the Zeek standard library for this. Let's see, lib standard random /Xoshiro. Come on, okay. Like it's really like it's not that big. Like it's almost tiny. Well, I wouldn't say tiny, but it's small at 150 lines. But I'm not sure if I even want to go that high. But maybe there's a. Okay, so a subset of the linear feedback shifts. Yeah, this itself is small enough. Why are there so many different bit versions of this? Like, can you only pick one? In which case, this is tiny. Like, how many times do you want to go through this? But no, this is helpful. Okay, this is, yeah, this is tiny. This is a tiny pseudo-random number generator. And yeah, clearly very fast too. Yeah, many variants too. Yeah, I guess since this is so simple, it would be straightforward just to test this out and just see if you just put something in, how like random does each state look like each time you go through this from the last. Okay, yeah, let's give this a go. Move this way. We wanted to do the Fischer-Yates. So let's try xorshift example. So let's see. Yeah, if we're going to initialize this with the nano timestamps, but like the nano part is rounded to like, I guess it really doesn't matter how much, it doesn't matter if the last couple of, if the nanoseconds are rounded to the nearest 100, since everything else is sufficiently random. Okay. So we can do the 64-bit version. And basically, the code for each of these is basically the same, right? The only thing that's differing here is like the 32 here has been changed for 64. As far as, oh no, okay, I'm incorrect, I take that back. It is like 13.17.5 and then like 13.7.17. There are some slight variations. Okay. All right, so I guess we just want to say, yeah, this like xorshift, it's a function, and we'll just take in a u64 int, and then we'll output a u64, and then it's just a matter of saying, for the first int, calculate this to be again, that doesn't matter in the scheme of things in terms of performance, but I wonder if I just use like Zig's variables, would the compiler pick it up? Or should I make everything constants? My inclination is to always make it constant. So yeah, so first of all we want to say int1 will be equal to int together with, what's the key? Let's make this simple. Let's make it simple. X2 should be X1 and X1 shift 13, and then make X3 X2 shift with X2 shift 7, and then X4 should be X3 with X3 17, and we'll see if you return X4. Oh, sweet, yeah. Yeah, I can, yeah, Sam says, could you email me the exact Dvorak layout? I want to make sure I accurately provide in the next 3 num released. Yeah, sure, I can do that. Because over these I have seen a number of variants, and yeah, I don't know all of the variants off the top of my head, but I can send you the one that I'm using. Okay. Okay, so once we have that, then we'll want to plug, let's just test this out. So let's get our micro timestamp and test it. So we get this, and then we want to say dprint timestamp 1, and just have this as the micro timestamp. And then, actually, let's call it like T1 is the micro timestamp. And then we just want to say T2 is equal to, I mean, like this is programming, we may as well use a for loop. So let's call this like xorshift. At least if this isn't the name of it. xorshift value is equal to the micro timestamp. And let's just do, say, like 10 iterations of this. We want to say, we want to just print out the current value, current xorshift value. I'm also using this a new keyboard that's just a temporary keyboard that's not mechanical, and it has its issues. Print that out, and then we want to update it. But I seem to be missing something. Okay. Okay, let's run this. The Fischer-Yates. Oh, expected E64, found I64. Yeah. It's because we want to bitcast it. I mean, like, yeah, not that I'm any good at like telling if stuff looks really random, but this looks alright to me. If we run this a couple more times. Well, okay, now you can kind of see how it's a bit predictable. we got something like 500, 156, and now it's like also 500, 180. Guess you do need to go through it a couple of times before you get something sufficiently different. So maybe we do this like 10 times and then it's all right. In either case. Okay, I think then that's enough to start to implement this shuffle. Oh, it's nearly 1 a.m. Okay. Can I do this in half an hour more? Should I do this in half an hour more? Okay, so let's say we take in some like an array of dedicated size. So and then an array of bytes. You want to return a similar array. How should we begin this? So I think from this kind of experiment, I get the feeling if we run the xorshift, say like 10 times, we'll get something that should be like random enough. So each time we'll get like, for each step in this, we'll get the, well, let's see, for 0 up to n, well, we want to construct a new array first. So we'll call this like list1, call list2 to be an u8, make it undefined. So from 0 to n, hang on. How are we going to mark if, well, it's like a nice way of like popping something off from this array. I guess we can just remove something from the array and then shift everything down, and then it should still be fine. So we want to get a random byte first. So if we do, we can adapt like get randomish byte up to include the xorshift. In fact, I think we can modify the get randomish byte to do this, yeah. Note, using just the timestamp, repeated calls of this function if using just the timestamp will not be very random. As such, we pass it through xorshift 10 times. well, many times. Okay, so we got the byte. Pass remain. The timestamp is the converted timestamp is the thing that we want to pass through it heaps of times. So yeah, we can say XOR input is equal to this converted timestamp, and then let's say xorshift xorshift number, make this a 10, and then for the 0 up to that, the XOR input is equal to XORShift of the XOR input. Then we want to choose the last, choose the last bits, provided the last bits are sufficiently random. Or maybe it's actually better to choose like, I was gonna say like if we choose like the first bits, like these are always going to be the same generally, but then maybe the XOR shift makes it sufficiently random. But then if we choose the last couple, if those have been rounded in some way, then we'll choose the last ones. So we want to say the last byte. Say the random byte is equal to truncate. Truncate the XOR input. And then we want to return the random byte. Okay, so that gives us a randomish byte, and then that should be different each time we call it. Then we can use this randomly byte up to get us a limit. So now we can use that in this Fischer-Yates. So we want to say, like I want to take a bit of care when doing this, like the popping, but it should be fine. But conceptually it is clear, just like knock something off and then move everything down. Unless we could do this via slices in some way, maybe. I also don't want to use like unnecessary internal sig structures. Although there are many helpful zig lists in which you can pop and add elements. I think it's okay. Again, if it's going into the Serenum, we want to keep it simple. So I think for 0 to n, we want to say, if for 0 to n, we want to say the random int is going to be get randomish byte up to the limit, which should be n minus I. That will give us something random in the array, so then we want to pick that. The random element is going to be list 1. We're going to have to cast this, maybe. see if the compiler yells at us. Then well, list to I should equal that random element. And then we want to shift everything accordingly in the list. So now we want to say for we just do a mem. Can we do a mem copy? We should be able to. I want to say for list 1 from rint to n minus, yeah, it should be n minus I. We want to be copying, n minus I minus 1. We want to be copying everything slightly above it. Rint plus 1 to n minus I. Okay. And then we want to return, well, I guess if we were doing this at comp time, we would need to make like a final list 2, but we can just return list 2 at the end of this. Okay. Let's go to this. Okay, so now let's say yeah, like list A is equal to, I guess we can make this constant. Yeah, let's say we just have 1, 2, 3, 4, 5. And then we just say list B is equal to Fischer-Yates list A. List C is equal to the same thing. And then we can just see how sufficiently random they are. Let's put spaces between all of these. List B, list C, list D. Okay. Seed run Fischer-Yates. Oh. 50. Oh yeah, we do need to provide 2. We need to provide the size of it. Okay, the issue I thought we would have, we are getting. We must convert things to usize. Oh no, it's the other way around. Oh, it's things I is usize. Cannot mem copy a constant pointer. Yeah, that is an issue. Because this is meant to, both of these is meant to, oh, what? Yeah, actually, we'll call this one the original list, and then we'll say list 1 is equal to the original list. No format without a specifier. Oh, it wants some any's in here. Oh no, it's the same thing each time. That's a bit embarrassing. Oh no, and then we gotta. Wow, okay. So it works the first time and then we just get, what are these issues? Mem copy arguments alias. Oh, okay, this mem copy isn't going to allow us to have overlapping memory, which is very fair. Very, very fair. Okay, yeah. Memory regions not allowed to overlap. Okay. Sure. I guess we can just do this with a really boring loop. For what? For rint going up to minus I minus 1. We need to get like the, this is fine, this is fine. Then we just want to say list 1j is equal to list 1j plus 1. I think that's all it is. Okay. Okay, suddenly no memory dumps. Okay, at least per round, these Fischer-Yates shuffles seem to be fine, but this is the same list shuffled. Why? So how to use a PC without a seat? I guess I'm just, I do a lot of running, I do a lot of walking, I'm just on my feet all day. What can I say? Maybe I should take some more breaks and walk around, but it's what I get used to. Okay. Okay, so in some sense, this is the fact that each of these shuffles is different per core is like, I'm kind of happy enough to add this to the game. This will be very easy to transfer to the Serenum. Very understandable, pretty simple. But I want to fix this issue that each time that we're calling what should give us a random shuffle is giving us the same shuffle each time. Like, this totally sucks. Let's correct this. So, yeah, why is this failing so hard? So since we're calling an external call for the timestamp, this can't be, it's not like this is being done at comp time. It really is. It's like get randomish byte is not random enough. Part of me is just like, really? Like it's, I almost want to just do a super crude thing of just printing out what this even is. Like, is it the case that the sequence we get in each of these cases is the same? It's not even a setup at this point. It's like an ATM machine with Windows installed. Yeah, yeah. Okay, so maybe I'm doing something really silly in the code then. Okay, so simply adding in a time delay with the file I/O for the program to just be writing this to the screen is like enough to sufficiently make these things random, or slightly more random. Like there's barely a difference between those shuffles, but there is a noticeable one there. Okay, and then we're like back to almost the same. And kind of disastrously here, the spacing in between. Okay. Like, yeah, clearly there's a correlation between these numbers and this. Like, yeah, we had total repeats in that, so we had repeats of these shuffles. Here it's like randomish enough between those two that we get different shuffles. Okay, so the timing really is an issue. Since all of this is being determined by the micro timestamp, this suggests to me that when this is executing, it's executing faster than a microsecond, which is good. Like, Zig is a performant language. If this is Python, this would not be the case. So maybe we simply just change this to get a nano timestamp instead. From memory, the nano timestamp was like 128. So we will need to truncate this and then cast it. So let's just say so we just say like nano truncated, or make this an I64, and then truncate this. And then we can convert that. Okay. Hopefully this should well, not quite. No, it hasn't solved the problem. These are the same, basically the same. So curiously, maybe like calling this function 3 times is enough to get a like timing difference, but 2 of these always seem to be repeated. Like now it's these 2 are repeated, but otherwise it was those 2. Okay, and now they're like all the same. So I think all of this is just telling me that anytime we're calling like Fischer-Yates, it should be from some kind of like randomish thing that we just continue to update. Since the timing here is too quick. Zig is too fast. But part of me is just like, really? Like I could also see that just since this is like the Windows, well, what's Zig doing? We can look into it. Yeah, it says like on Windows this has a maximum granularity of 100 nanoseconds. And so if I do like this PC, well anyway, I think most PCs have processors that work at the gigahertz level. Let's just see how many instructions do like modern CPUs, or like what's the clock rate of modern CPUs? Like yeah, I can totally see that with like a granularity of 100, Zig has the code, like yeah, the compiled code is efficient enough that what gets run here, especially since we're just doing lists of like 5 elements, mean that even if we're doing like a remainder operation in here, two of the new nanoseconds polled are within the 100 nanosecond difference. Yeah, so especially if it's, if we're doing 32 billion a second, yeah, this tracks. Okay, in either case, I'm satisfied with what we've done tonight. Yeah, I think this should be enough. Yeah, we've now got something that we can transfer to the Serenum easily, or relatively easily. And yeah, if I actually wanted to make like the Fischer-Yates here not spit out the same thing, the solution is just to feed into this get randomish byte some like pointer to the same pseudo-random number generator that we update each time. And then this way, when we run it through xorshift a couple times, it will be different each time, and then we'll get sufficiently different shuffles. It should be fine. Okay. I should like, I should put some comments here. Oh. Extremely crude O2 Fischer-Yates, and pseudo random number generator code. Absolutely not okay for production code of any sort. Basically a sketch draft. But you know, I can't help myself. It may be better than the 25 years of Java's. This was so wild. No, where was it? Where was the Java of Java's? Of Java's LC computer. Okay. Let's save this and what's it? LSAL. This one. Yeah, we want to git add Fischer-Yates. Played around with Fischer-Yates. Shuffle. Hello, hello Kudra. Unfortunately, I'm basically wrapping up the stream. However, everything I do on stream is publicly accessible on GitHub. Go to github.com loaded and go to the repositories. The current project I'm working on is a really simple sliding puzzle game in Zig. In particular, it looks like this at the moment. You know, very simple. I think I put around 8 or 9 hours into it. At this stage, we're making it basically from scratch, like no significantly external libraries for this. Yeah, we're just using no. We're just using where's main? Where's main.zig? Wait, and now I'm confused. Where has the source code for our game gone? Did we accidentally delete it? Or did I just call it something weird? What is it called? Okay, now I'm like concerned. Yeah, it should just be called. Where's the? Yeah, the root source should be called main.zig. So this error should say it's not finding main.zig. Okay, I thought I was going to end the stream, but I guess not. I guess I need to recover the file I just overwrote. What? Why is main.zig not here? Why can't I see this? None of these are called main.zig. Oh, it is late. Okay, it's here. Why isn't it? If I can see it here, Why can I not see it here? Like what? Is GitHub just like screwing up in? Oh, okay. It says view all files. Okay. My bad. Okay. Anyway, I just wanted to say all of the main code of the game that did the code of this is all online. It's it's a smallish file. We're like less than 600 lines so far. And all of the libraries we're doing have been, technically they were written in C, but have been adapted to Zig. Just ZOpenGL and ZGLFW. But yeah, that's it. So yeah, thanks around. Thanks for everyone who stopped by this stream, said hi, said some comments. And yeah, next time we will transfer all of the super draft Fischer-Yates algorithm and eliminate from this code the Zig random pseudo number generator, and then we'll probably get onto calling. Yeah, we'll get rid of all of this stuff, and then get onto mapping some textures onto the faces of these. That's the code for that. Will probably be a bit fiddly, since it's different from just rendering like a single a bunch of separate textures onto polygons in OpenGL. Like we'll have to think about how to there's going to have to be some coordinate transformations, but we'll cross that bridge when we come to it. But yeah, otherwise, have a good afternoon, night, evening, morning, whatever time of day it is. Bye bye.